Okay, I think we'll get started. Hi, everyone. My name is Kelly Dudley, and I'm with the New Center, and I'd like to welcome you to today's webinar entitled Utilizing ACI Code 323, Low Carbon Concrete, Real World Implementation and Examples. We're so glad you could join us. A video recording and PDF of the presentation you're about to see will be uploaded to the new website, newconcrete.org, following today's webinar. Attendees are in listen-only mode. You will have an opportunity to ask questions via the Q&A dialog box at the end of this presentation. The ideas expressed in the following presentation are those of the speaker and do not necessarily reflect the views of New Center, ACI, or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mix components, among other things. You should consult your materials, cement, and concrete professionals for assistance regarding concrete production or placement. Nothing contained herein shall be considered or construed as a warranty or guarantee, either expressed or implied, including any warranty of fitness to a particular purpose. Now, I'd like to introduce you to our technical director and our executive director.
Hello, everyone. My name is Sureka Sumanasuriya, and I'm the Technical Director for NEO. And thanks again for joining the webinar today. There's a lot to learn about ACI 323 code, and I will be here helping with the Q&A with Kerry. Kerry, I will let you introduce.
Thanks, Sureka. My name is Carrie Sutton. I'm the Executive Director for NEW. I'm going to introduce our speaker today, Nathan Forrest. Really appreciate Nathan taking time out of his schedule to give us this presentation. So Nathan is the Technical Director at the California-Nevada Cement Association, where he leads innovation in low-carbon concrete technologies. He's recognized as an authority in the use of blended cements, low-carbon concrete materials, codes, and specifications. And he plays a pivotal role in major projects throughout California. So Nathan is based out of California. And he is also a member of the ACI 323 committee, and he's a member of the new board. So thank you, Nathan. We really appreciate your time today and look forward to your presentation. Thanks.
Thank you, Carrie. Appreciate you having me out today to talk about today's topic, ACI 323, what it is and why it is and where we're going with it. So some of the items we're going to cover with the agenda here are showing up on the screen, and we're going to get right into it pretty quickly here. Why do we need low carbon concrete? For many in the audience today, this will be a refresher, but the gist of it is that building materials account for about 11% of global CO2. And we often hear repeated that cement and concrete are responsible for about 8% of global CO2 emissions, although here in the US, that's about 1%. But also, when we talk about building construction, concrete is often responsible for over a third of the embodied carbon in the building. Some terms we're going to talk about as we move along through our presentation here. So what is embodied carbon? It's a way that we can measure the greenhouse gases released through the manufacture, transport, and installation of a product or material. In the context of ACI 323 and generally for construction materials, the term embodied carbon refers to this portion of the graphic over on the left side, the A1 to A3 product stage of the development of a material. So that includes things like raw materials, processing, sourcing, manufacturing, transporting, etc. It does not include construction. It does not include the life cycle using the product in place. Doesn't include the end of life, and it doesn't include the concept of a circular economy. Those are all great things, but ultimately outside the scope of the code that we're going to talk about today. We also often use the term global warming potential, or GWP. And what that means in this context is that when we talk about the manufacture of materials, there are a lot more global warming gases that can be emitted than just carbon dioxide. So we take all of those gases and normalize them to 1 unit, or kilogram in this case, of carbon dioxide, and we use this term kilograms of CO2 equivalent per unit. Now, in the case of cement, that unit is a metric ton. In the case of concrete, it can either be expressed in cubic yards or cubic meters. Be careful with those units because they are not the same size. Now, when we begin to talk about carbon or GWP in concrete, we have to talk about how we manufacture cement to understand where this carbon comes from. So moving from our left to our right, we begin by excavating materials, raw materials from the earth that go into making cement. It happens in very large limestone quarries like this one that happens to be Cal Portland's Oro Grande quarry north of Victorville, California. This is a very large quarry, about 3/4 of a mile across. And limestone is what's being mined here. Limestone is the primary ingredient for making cement. We also need sources of iron, silica, and alumina as part of this. Sometimes cement plants have all of those materials on site, and other times they need to be imported. Now, following the extraction of these materials, they get crushed down into smaller sizes and then ground in what's called a raw feed mill down to a very fine powder, almost like baby powder, and then put into a kiln. This is a cement kiln. A cement kiln is a steel tube lined with refractory brick that's typically 8 to 10 or 12 feet in diameter and a couple of 100 feet long. It rotates slowly about its long axis. In this case, it's inclined from our left to our right, the right end being downhill. And the material, the limestone and other raw materials, are fed into the uphill end of the kiln. And because of that rotation about its long axis, the material slowly slides down the inside of the kiln, getting hotter and hotter toward the bottom end as it approaches the burner in the bottom. This is what a cement kiln looks like while it's operating. And down on the bottom, circled in blue, is the product coming out of the kiln called clinker. We'll come back to that in a moment. Now, inside the kiln, there's a few things going on that we need to understand. Primarily, in the second line there, we have what we call process-related emissions. And that's where we're taking calcium carbonate, also known as limestone, also known as CaCO3, also known as Tums if you get heartburn like I do, and we are thermally decomposing it into calcium oxide, CaO, the primary building block for cement, and carbon dioxide, or CO2, with its global warming potential that we're concerned about. Now, what would not be obvious at all is that if you were to pick up a rock of limestone, have some here in a little jar, that limestone is 44% carbon dioxide by mass. And we would think of it as a solid rock, but when that limestone is ground finely and heated up, that carbon dioxide gets driven off to make that calcium oxide. And that's responsible for most of the CO2 that comes from cement production. Even if we had electrical kilns or hydrogen fueled kilns or something like this, we'd still have most of the carbon dioxide associated with this. And that's what makes this industry so challenging to decarbonize. And the reason, here's what the clinker looks like after it comes out of the kiln. It's going to be on its way to making cement in a minute. In the finishing mill that looks like this is where we're making cement out of that clinker. We're combining the clinker with some other materials to make either ordinary Portland cements or blended cements, which can be a fantastic lever for reducing the carbon footprint of the concrete that the cement makes. That's a topic for another day, though. The reason that we care so much about how we make cement and the carbon impact that comes from making cement is because of its impact on the concrete's global warming potential. While cement might only be 12% of the mass of concrete, it's responsible for up to 90% of the GWP of that concrete. And so by focusing on being efficient with making cement, e.g. through blended cements, we can be much more efficient in making concrete. Now let's talk about ACI 323. So why did the American Concrete Institute want to develop a low carbon concrete code? Well, they looked around and realized that other entities and agencies were taking action without input from ACI and largely without input from the concrete industry. In 2019, Marin County, California passed a low carbon concrete code. ASHRAE has talked about introducing low carbon requirements for the International Green Construction Code. Carbon Leadership Forum, National Resource Defense Council, New Building Institute, RMI, formerly the Rocky Mountain Institute, now just RMI. Other nonprofit organizations have been doing a lot of actions regarding low carbon concrete. Here where I live in California, the Cal Green Code was introduced some couple years back and is now the law of the land. So all non-residential buildings over 50,000 square feet have to comply with carbon requirements or whole building life cycle analyses. We also saw a lot of action at federal agencies like the General Services, Environmental Protection, Federal Highways. Much of that has been paused under the current administration, but those things were moving along very quickly at the time ACI decided to do this. You'll notice here, though, among all of these other agencies taking actions, there was not a lot of certainty around the term low carbon, what that really means, and what that means to the concrete industry. So ACI authorized the development of this code committee to proceed with developing a code. Here we are, the code committee for this. We have representatives from consulting, we have representatives from the cement industry, from academia, from structural engineering, from federal agencies, from contractors, folks from ACI staff, a really well-rounded group of people that were pulled together to develop this low carbon concrete code. It happened very quickly. Our first meeting was at the San Francisco ACI conference in the spring of 2023, followed thereafter by a full day workshop, really a day and a half, at ACI headquarters in Detroit, Michigan. That's where the photo on the previous slide was taken. And then the code committee kept working through this language and ultimately published the ACI 323 code in October of 2024. Some of the key tenets that you're going to see as recurring themes as we talk our way through how this code is put together, it expresses the primacy of life safety. The low carbon requirements are always going to be secondary to the requirements of durability, serviceability, life safety, etc. In no way does the implementation of low carbon concrete compromise any of that. We do not prescribe concrete mixes. It's not going to tell you use this mix, use this much SCM or fly ash or slag, whatever your favorite SCM is. It's not going to tell you to limit cement. It uses a carbon budget approach, which means that you don't have requirements for a mix by mix compliance, but rather you look at the carbon throughout the whole project. And I'm going to show you examples of how that works. Here are some of the constraints that the committee faced. ACI had set this aggressive timeline of completing this goal in completing the code within 2024. So we didn't have time to do a lot of research in this. We had to lean on what was already available. We also had to have it, since codes are mandatory language, it had to be applicable to all sorts of building projects. And we had to lean, again, on the data we have compared to the data we want. That drove, again, more of the limitations in this code. Let's take a look now at how the code is structured. It has 8 chapters plus a couple of appendices. We're going to walk through how these chapters work and what you'll find in each one of them. So just like most ACI codes, Chapter 1 is kind of some general information. It talks about what the purpose of the code is, where it's applicable, where it's not applicable, who has control of this. What we'll find is that it says the licensed design professional, a term defined in Chapter 2, shall be permitted to specify more stringent requirements in the code, but not less stringent. But as you'll see later on, the adopting authority of the code can waive provisions of the code if it feels that they're not in the interest of the public interest to do that. So the code does not apply to concrete less than 2,500 psi or greater than 8,000 psi. It doesn't apply to precast, auger cast, or shotcrete, and that's again because the data that we had available to use relative to the data that we want. Toward the end of the presentation, I'll talk about how we may be looking to improve that, but for now, that's where we have. Again, the code is not intended where compliance might compromise required strength, stability, or serviceability. And as I mentioned previously, the requirements of the code can be limited or excluded if the authority having jurisdiction or entity adopting the code determines requirements are not feasible. Chapter 2 defines some terms here. The licensed design professional is essentially the architect or engineer who's putting their license on this project and is responsible for determining or ensuring code compliance. Chapter 3 has some reference standards. It's all about ISO and standards about environmental product declarations and product category rules associated with those EPDs. Chapter 4, again, talks about what the scope of the code is, applies to concrete mixture materials, talks about these upfront embodied carbon, again, life stage A1 to A3. Again, the licensed design professional specifies the reduction, uses a carbon budget approach, and it does have this final bullet, consideration of regionality. The code does encourage the adopting agency to establish their own benchmark, and in the absence of that, can use NRMCA regional benchmarks, which are made part of the code in Appendix A. Note that NRMCA document that we'll look briefly at only covers the lower 48 states, so any project outside of there is going to have to establish its own benchmark to use the code. Also in Chapter 4, you see a description of this carbon budget approach. Don't let the summation symbols and the math here deter you. I'm going to show you how this works, and you'll see that it is not complicated. Chapters 5 through 8 break down what kinds of projects this code is applicable to. So Chapter 5 covers buildings, and we evaluate the size of the project on the basis of gross floor area. Chapter 6 is for pavements and hardscapes, where we look at concrete volumes. Chapter 7 is for bridges, where we look at the area of the bridge deck. And Chapter 8 is for other structures, where we're also looking at concrete volumes. And then within each of those chapters, the code breaks the projects down into Tier 1, Tier 2, and Tier 3, which are essentially large, medium, and small projects, as you can see by the size limits of the projects shown in the table here. So the structure of chapters 5 through 8 is all very similar. You'll find a table just like this one on the left in each of those 4 chapters. You'll see a couple of code sections, 532, 533, are very similar. Code section 632 and 633 look just like these. So do 732, 733, 832, 833, etc. You'll notice right here that this code uses alpha as a carbon reduction factor. If an adopting agency is going to use the NRMCA regional benchmarks, the reduction factor is 0.85. But the code does encourage adopting agencies to consider determining what their own appropriate reduction factor is. So it's clear that we're going to have to measure the carbon in our concrete to be able to do this. And the way that we do that in the concrete industry is through the use of environmental product declarations. Just as the image here suggests, it's not unlike a nutrition label for concrete, except that instead of talking about calories and fat and carbohydrates and protein, we talk about global warming potential and eutrophication potential and primary energy usage and other required metrics like this. In the concrete world, each unique concrete mix is a product, and so we're talking about environmental product declarations. Each mix can have its own environmental product declaration, or EPD. And so on a large and complicated project, you could have many, many EPDs, dozens, perhaps even 100 on a really big project. The industry average EPD is a document published by the National Ready Mix Concrete Association. It's a really useful document for understanding impacts in the absence of a lot of other information, but it does not have a place for code compliance with ACI 323. Chapter 4 calls for facility-specific or product-specific environmental product declarations or life cycle analyses. So we're going to need to use product-specific EPDs. This is an example from one in the greater Los Angeles area. What you'll find is that it's an EPD for a specific mix design at a specific compressive strength from a specific plant. It's got its date of issue, which is valid for 5 years, and this one's actually expired. And it tells us what our global warming potential is in units of kilograms CO2 per cubic meter, in this case, 247. Who has environmental product declarations available? Take a look at this map from buildingtransparency.org. When it initially populates that link, it's a little confusing to look at. Just double click on the top one, ready mix concrete, and you will see only dots corresponding to ready mix concrete facilities that have generated facility specific environmental product declarations. Here where I live in California, about 40% of the concrete plants have generated facility specific EPDs. If you're in another part of the US, your mileage may vary. It appears that the cowboys in Wyoming and South Dakota are not terribly interested in this at the moment. I mentioned the NRMCA earlier, National Ready Mix Concrete Association. They also publish a regional benchmark report, which breaks the United States down into 8 regions and has benchmarks for 5 classes of concrete plus lightweight concrete, 3 more classes of lightweight concrete. So again, use of this as the benchmark for code compliance is permitted, but the preference is for the agencies to establish their own benchmarks. We're going to look at a table from this code and an example coming up here in a minute. So now I want to take a look at how compliance looks and how it works on 3 different projects. I'm going to go from small to medium to large, or tier 3, tier 2, tier 1, to see how it works in increasing scope and complexity for compliance. The first project we'll take a look at here is a Starbucks drive-through in Denver, Colorado. This drive-through lane is 255 feet long, 11 feet wide, 6-inch thick pavement, grand total of 52 cubic yards. I don't think anybody's buying a vacation home based on this project. We have some F2 exposure for freeze thaw there in Denver, and they drew perhaps a bad hand on their sulfate conditions. They got an S3 exposure here. So the bottom 2 bullets here, we're going to have some requirements out of ACI 318 Chapter 19 durability requirements that we'll see here in a minute. So we said this project was 52 cubic yards. We look at table 6.3.1. We see, in fact, it is a tier 3 project. We have no GWP limits, and our documentation requirement is found in section 6.3.3 that you see on the right. Pavements and hardscapes, document concrete mixes, specify compressor, fractional strength, durability strength, other performance requirements, and a summary of any strategies used to reduce the GWP of the concrete on the project, a narrative. So we're going to get our mix design here. I found one. This is from Aggregate Industries in the Denver area. We're going to see that it has 20% fly ash. It has an air and train admixture, has an air content 5 to 8%, has a water cement ratio of 0.41, and it's 4,500 PSI compressive strength at 28 days. That satisfies all of those needs that we had for the durability requirements. So the licensed design professional is going to be collecting this documentation, right? Concrete uses, concrete strengths, durability requirements, other performance requirements, mixed design, material sources, gradations, test results, all real standard stuff, right? We also have this summary of strategies to reduce the GWP of the concrete on the project. We can say something like the concrete mix and construction was optimized by replacing 20% of the cement with the fly ash and sourcing locally, right? Obtaining materials from local suppliers to reduce carbon emissions associated with transportation. Did our building code, ACI 318, say that we had to have 20% fly ash? Yes. Can we also take credit for it, for reducing the carbon on the project with it? Yes, that's okay. That choice to use that method to comply with the code did result in a reduction in the carbon. As far as sourcing locally goes, that's a very standard practice in the concrete industry. With regards to folks that do have imported aggregates, most aggregates, come from very local sources, and so we use them and reduce transportation costs and emissions. Next up, we'll take a look at a medium-sized project. This is the Foothill Low Water Crossing Bridge in Cuyama, California. Serves as an alternate route to State Route 166, which is very prone to flooding. This bridge is 650 feet long and 36 feet wide, so we have 23,400 square feet of deck space on the bridge. Take a look again, table 7.3.1, and we see that for a bridge between 5,000 and 25,000 square feet, it is a tier 2 project. Again, we have no GWP limit, but we do have a little bit more documentation requirements. So in addition to that 0.3.3 paragraph that required that summary, we also have the 7.3.2 paragraph, which requires us to figure out what the GWP project average is, the benchmark average, and the individual, and report the individual benchmark values and project values for each class of concrete on the project. So again, we're going to need facility-specific or product-specific environmental product declarations or third-party verified LCAs, right? Those are the means to comply with this documentation requirement. So we're going to start with information from the designer. We need to understand what the concrete mix types are, how much of each type of concrete is going to be used on the project, and what the required compressive strength is so that we can associate those concretes with the classes of concretes in the benchmark report. Next up, we'll take a look at information from the National Ready Mix Concrete Association, the Pacific Southwest, regional average GWP values. And to that, we would add project GWP values, this information, again, from the EPDs that come from the ready mix producer. And so in code terms, we have the individual volumes, the individual benchmark GWPs, and the individual project GWPs. So we're good on that front. Then we've got a little bit of math to do to figure out what the GWP project average is. So in this case, we're multiplying the 700 times the 298, the 50 times the 315, the 600 times the 340, et cetera, and then dividing by the total volume, the 700 plus the 50 plus the 600, et cetera. And we arrive at 312.9 kilograms CO2 equivalent per cubic yard in this case. Next up, we do the same exercise looking at the benchmark values, and we come up with 247.1 kilograms CO2 equivalent per cubic yard. And finally, we compare the ratio of those two. The ratio of our project average to our benchmark average is 1.27. So what that tells us is the concrete on this project has 27% higher GWP than the industry average. Is that okay? Yes, because what was our required GWP? There wasn't one. But we do still have to have a written description of strategies used to reduce GWP on a Tier 2 project, just like we did on Tier 3. Finally, let's look at a large project, an office building, this one in El Segundo, California, 60,000 square feet. Take a look at table 531. We see that greater than or equal to 50,000 square feet is in fact a Tier 1 project. And now we do have a GWP limit. We see that our GWP project average has to be less than or equal to our reduction coefficient, alpha, that we talked about earlier, times the GWP benchmark average, and we have the same documentation requirements as we did on a Tier 2 project. So we're going to start off by looking at all that, just like before. We're going to look at the benchmark reports, again, in the appendix, information from NRMCA. That's going to be important for our calculations, just like it was in our previous example. We're going to get information from our designer, all of our concrete mixes, our uses, our volumes, our exposure categories, strengths, et cetera, et cetera. To this, we're going to add information from our ready mix producer in the red box here, right? Based on environmental product declarations. Now, in the green box, I'm adding the benchmark values from NRMCA regional average report. And then to that, I'm adding another column that has 85% of those values as called for in ACI 323 when we're using the default values. And then we can run through the same sort of mathematical exercise and figure out what the total GWP is for each of those columns. We do a little bit more math, looking at the total GWP divided by the volume of the concrete on the project, and get a benchmark average of 264.82. We look at our EPD values added up, divided by the volume of the concrete. We get a project average of 223.98. So we're good on those two reporting items. And then we compare our project average to our benchmark value and find that we are at 84.6% of the benchmark. And recall that for compliance, we needed to be less than or equal to 0.85. So we have compliance. We're less than 85%. So we had 11 total mixes, 3 of which exceeded the benchmark, some of which were lightweight, and those being higher than the benchmark values were just fine. We are in compliance. And recall that we still have this written description, just like we did in Tier 2 and Tier 3. And so what is next? Well, what's next for designers is that they need to begin requesting or requiring environmental product declarations to get comfortable with using these values and reporting on these values. You should be developing specification language, or if you need help with specification language, I'm here to help you to reduce the GWP in the concrete and get familiar with ACI's resources on this. The QR code on the right, I'll leave up here for just another moment in case anybody wants to snap a picture with their phone. I checked earlier, it works. Will take you to ACI's global warming potential calculation spreadsheet that was put together for compliance with this code. Makes life real easy for you. You don't have to develop your own spreadsheet like I did because I did this before this spreadsheet existed. What's next for the code itself? Well, the code committee is already working on ACI 323-29. We have formed 7 subcommittees here that you see on the screen to look at updates and improvements to various sections of the code. If this sort of thing interests you, I would encourage you to come on out to the ACI 323 committee meeting at the ACI convention coming up in Chicago. I think it's in Chicago. And what's next for outreach and adoption? The ACI Code Advocacy Group is working to position ACI 323 as the go-to for International Green Construction Code for low carbon applications. NEW is working on developing documentation, training, and outreach efforts for folks interested in adopting this. For jurisdictions and agencies, ACI offers free code access. So if you work at a public agency, like you have a .gov email address, reach out to me, reach out to ACI, reach out to NEW. They will get you free access to this code and are more than interested in supporting you in aligning your decarbonization goals with this code and showing you how to do local benchmarking and working with you to implement this code in your jurisdiction. So that's all that I prepared for this, but I think we're going to have time for some questions here. I haven't been paying any attention to the chat or to the Q&A, but I think I've got some help with this.
Yeah, we'll help you with that, Nathan. Good job. It was a very good overview. I think one of the things that I just in noting is you know, the flexibility and the simplicity of the code. I think a lot of folks are very interested in moving forward with this type of an approach. But one of the things you mentioned is that, and I think you could probably share more within the committee, is the flexibility of the code. You can adopt the code, portions of the code, whatever works for where your jurisdiction is at. So knowing that, I guess I'll throw out this question. One of the questions I had for you was, I guess, what do you see are some of the barriers to actually working with some of the maybe jurisdictions you work with to utilizing this code or moving forward with this type of looking at lowering the embodied carbon of the concrete in their projects? What do you think are some of the biggest barriers for these agencies and some of these authorities?
Well, clearly it takes, a lot of will on the part of an agency to want to do this. We saw that at Marin County in 2019. We saw that at the city of Santa Monica in 2024, which has also adopted a low carbon concrete code, and the city of Dublin also in 2024. Those are all California agencies. One of the takeaways from talking with the staff at Marin County once they adopted this code is they realized that this is an entirely different set of nomenclature and language than their building department officials speak. So it required a lot of education for the staff to be able to understand what all these terms are, right? We in the concrete industry and the sustainability industry, we throw these terms around, GWP and carbon and EPDs and cement limits and SCMs and all these sorts of things, and it's kind of second nature to a lot of folks that are very close to this. But we need to realize that this is far, far from the type of reviews that architects in many cases are used to, and many engineers don't speak this language, and building officials don't speak this language, and the folks submitting, asking for permits in these agencies don't speak this language. And so there's a big educational need out there. Marin County recognized that, and it actually caused them to delay implementing their code for some time. COVID, I think, intervened as well. But they had to get their own staff and the contractors and designers and ready-mix producers in their market up to speed.
Yeah, that's good. I mean, in the examples you showed 3 specific different projects, but I think it makes the point with, a very small project like the one you showed there with the Starbucks with a limited amount of concrete. I mean, you don't want to make it too complex, right? And
Right.
this code allows, across the board, anybody who picks it up and specifies it or uses it, that flexibility to say, all we want to do is, have you do the best you can to use the materials in your area and show that you've made some type of attempt to lower your embodied carbon. And then as you get to more complex projects, as this code does, it starts to require more of the reporting and the actual looking at the whole project and looking at ways to strategize for lowering embodied carbon. So I think that was a great move upon the committee to
So
not overwhelm.
that's right. And on that note, Carrie, I would repeat that the design professional always does have the option to put in a more stringent requirement. So, if the owner team, the contractor team, et cetera, is interested in moving the needle, even on a small project, they could put in a reduction factor of 85% or more, right?
Sure.
They could say they want it to be even lower than that. The code just it doesn't allow a less stringent implementation without the code adopting agency agreeing.
Good point. That's the flexibility of having a standard like this that can
And
be
I'll
adopted.
also note that while this is structured to be building code language, there isn't anything stopping somebody from using these principles and these concepts on private work. In fact, I've seen this code language on private projects.
Good point. Very good point. A question on the future work of the committee to, I mean, this code was um, put together and you showed some of the things that it does not cover. It had to start at a certain level and bring in, but I know a lot of the areas you mentioned where you're looking possibly in the future, and I'm sure there's reasons for that, but
Mhm.
most likely maybe you can explain a little bit about how some of those other items could be potentially brought into the code later on as you develop it.
Yeah, there's been some recent work done by Jonathan Broyles and Michaela. Boy, I apologize, Michaela, if you're out there. I'm just drawing a blank on your last name. They did a really nice presentation at Carbon Leadership Forum last week. And they looked into a lot of detail into data in EC3 and were able to break out a lot of information about concrete applications. As it stands, all the concrete it talked about in this code and talked about in the NRMCA regional benchmark report. It's all related to compressive strength and makes no distinction between, a pile and a retaining wall and a shear wall and a pre-stressed floor slab, right? They're all just 4,000 PSI, for example. And we know very clearly that those are not the same concretes. On a deep foundation, we kind of don't care if the concrete takes 42 days or 56 days or 90 days or whatever to get to its ultimate strength. But if you're in vertical construction and looking to advance to the next floor and the next floor, developing strength quickly is very important. And so being able to distinguish concrete applications, perhaps in a wider range of compressive strengths, those are really important things to be able to improve on what the code is instead of looking only through the lens of compressive strength.
Good point. Very good point. Sreka, I know you might have a question there, a couple that you're fielding.
Yes, we have a couple of questions. Let's see. You already talk about the jurisdictions, but
Yeah, and let me mention something about that, Sarika. I'll concede that the code uses the term authority having jurisdiction, but doesn't define that term. That was a miss on our part. That term comes from National Fire Protection, and it just means the building official, the city, the county, the state, whomever is adopting the code. It's unfortunate that we missed that. We'll look to correct that in a future edition.
okay. Thanks, Nate. And also, we have a question asking whether anyone has adopted the code yet or planning to. Even Kerry may know more.
I'm not aware, but I know Carrie's a little closer to this than I am.
Yeah, at this point, I mean, we've had folks that have that are referencing it in specifications and looking at it as a standalone code. I mean, always one of the big things you want to do is try to get it into a model code so it's accessible to everybody. But that doesn't mean jurisdictions can reference it or adopt it as a standalone code that maybe goes with a green code or part of another code or ordinance within their jurisdiction. So like any code, it takes a while to get through the process, but our objective obviously is to have it referenced directly in a model code, which then it would be available easily that way.
Thanks, Kerry. Next question. Does the ICF building technology follows exactly the same course you described?
I think you're talking about insulated concrete forms.
I believe so.
Yeah, certainly you could construct an ICF building under this code. Not just this code. You need other, design tools and code requirements as well. But you would just be in Chapter 5 for buildings, and depending on what size the building was and gross floor area, would tell you what tier it was and then what compliance methods were required in the code. But yeah, there's certainly nothing here to limit the use of this in an ICF application.
Absolutely.
Yeah, that's great. Thanks, Nate. All right, when GWP values for a product is not available, are there any regional averages or estimation to use in our calculation? And I'm more interested in GCC and MENA areas. I believe GCC stands for Gulf Cooperation Council, I believe, and Middle East and North
Yeah.
Africa.
So this would be the Middle East benchmarks.
Yeah. So yeah, obviously the NRMCA regional average report is only applicable in the lower 48 states. So any place else, you would have to establish what the local benchmark was by looking at the relative strength, compressive strength classes of concretes used in that area, and then determine what is an appropriate reduction factor from that local average value. So that's what the code is going to call for. And I'll apologize, not being familiar with what kind of standards and reports may exist for regions outside of the lower 48 and Canada. There's a lot of information for Canada as well.
Yeah. So that benchmark calculation seems to be probably one of the challenges for some of these agencies, how they go about that, and what's the best way to do that. But I know NRMCA is doing a lot in that realm to help educate folks as well as new. And I believe, is the code going to address that at all or provide any guidance on that?
Yeah, that is the landscape of Subcommittee C.
Okay.
And that I'm the chair of. So we haven't done a lot to date, and that's squarely on my shoulders. But it is to develop guidance for an agency on how to develop their own local benchmark and how to decide what is an appropriate reduction factor for their area. Yeah, that's something that we'd certainly recognize we need to work on and plan to have in the 2029 code edition.
Yeah, and that makes sense. I mean, we see because materials are, different across the world and within the US, the availability, local benchmarks are, is probably what, is the best way to go. But there needs to be some education and ways to do that properly. So good, Nathan, you have your work cut out for you on that.
Well, I've got an all-star team ready to go. It's just,
Alrighty.
just up to me to get everybody together and get to work.
Okay. Anything else, Sarika? Otherwise, we can
We
wrap
have
up here
more
a little.
questions.
Okay, go
Let's
ahead.
see.
All right.
This is related to, again, NRMCA benchmarks, kind of. So the question is the NRMCA GWP table you kindly showed in slides only goes up to about 6,000 to 7,000 PSI. If I'm not mistaken. How are GWP limits handled for higher strength mixtures like HPC or UHPC?
They're not. Yeah, the code specifically only covers 2,500 to 8,000 PSI concrete. In a future version of the NRMCA report may have more strength classes than that, but today it doesn't. And this code was written specifically for use with NRMCA version 3.2. So many of us have heard that NRMCA will be coming up with a new edition of this code soon. But this, sorry, not the code, well, a new edition of the benchmark report soon. But this code specifically references version 3.2. So certainly an adopting agency could make an exception to that if they wanted to use some other local benchmark or even an NRMCA benchmark if they wanted to do that. But at present, the way the code is structured, those other concretes outside of that range are not part of the code.
All right. Thank you, Nate, again. Right, we have more questions. I'm trying to, with the time, let's see. Maybe we kind of answered this question, but let's give it a try again. Can you comment on the take up or application of ACI 323 by federal agencies?
I am not aware of any uptake from any federal agency of this code.
Okay.
So I believe I believe there may have been some work with a couple of the agencies to look at updating their standards to reference 323. I know that was in the works with a couple of them. I'm not sure where it's at after, the administration came in, but yes, there definitely was some work in that area.
All right, this one probably easy answer. Should we have certain certification to be able to conduct these calculations and provide it for contractors or clients as a service?
Well, my humble estimation is that yes, I think people who are going to be doing this type of certification or project evaluation should have some sort of certification for this. Again, coming back to an explanation I offered earlier, this is not native language to many folks in the architecture, engineering, and construction community. And so I think that to be able to do this well, a common educational basis needs to be established. And that is something that NEW is working on, a certification for this.
Yeah, I believe in it. We can certainly help with that in future. That's again part of NEW's vision. This okay. One more question, but it's pretty long. Let
Oof.
me see whether I can read. Is there ongoing research regarding the integration of machine learning models and other variables such as regional energy, grid intensities, aggregate ethology, and industrial technology maturity to generate reliable synthetic EPDs? Furthermore, what are the current findings on the effectiveness of these models in mitigating the lack of localized life cycle inventories to enable the implication of the ACI 323 standard in data-poor regions?
Well, it sounds like there's a few things to unpack there.
Yeah, that's a good
Right.
question, though.
I think that the upfront portion of it regarding machine learning and so forth, yes, a lot of that is being done by companies that are EPD generators. Folks like One Click LCA and Athena and Climate Earth and several others. I don't mean to exclude anybody. There's just the ones that come to top of mind. You know, they are certainly using a lot of advanced technologies in how they are modeling EPDs. With regard to, you know, how different grids are working, you know, that's a separate but also included part of how an EPD comes together. The EPD practitioner looks at the energy consumption for a concrete plant, for example, over the course of a year, and then looks at the carbon footprint associated with that electrical energy from the grid, right? So they're taking this external input and it makes its way into the concrete EPD. I think there were more parts of that question. I don't know if we got to all of it. It was kind of a complex question.
A good one, though.
No, thanks. Thanks, Nate. All right. This is for information. Thank Nick. Nick posted ACI Committee 239F is specifically on UHPC sustainability, and they are working on how to tackle documenting GWP issues within the UHPC space.
Awesome.
So
Good.
that's great news.
Excellent.
Thank you.
Yeah,
Yes.
one thing I would mention on this front is a very interesting thing happens, particularly when we start talking about extremely high strength concretes like UHPC. It's almost a bell curve distribution of GWPs. When we get up into extremely high strength concretes, we're using a lot of other things besides Portland cement
Yeah.
to develop the strength in those. And so we see, you know, 18,000 PSI concrete that has a GWP that's very similar to like 2,000 PSI concrete. It's kind of a strange
Interesting.
GWPs there.
Interesting. Hopefully I'll incorporate it in the next version. Speaking of versions, what is it? 3-year? What's the next anticipated
It's on a
update to
5-year
the
code. Yeah, it's on a
5-year?
5-year code cycle, just like
Okay.
you know, all the other
Yep.
ACIs. So that's why we have, like, you know, ACI 318 is 2014, 2019, 25. Maybe they skipped one there. I don't know. And this will be the initial version was 2024. The forthcoming version is anticipated to be at 2029.
Okay. So we have a little bit of time yet. A lot of opportunity to add some more information and more items. So,
Yeah.
all right. Well, I think we got through most of the questions, Sarika, and we just wanted to thank Nathan again and great information. And if there are any other questions that we see here that didn't get answered, we'll field those and reply back to those folks who answered or asked those questions. And now Kelly came on to kind of wrap things up. And again, thanks everybody for attending. And we hope to see you at our next webinar, which Kelly will announce here in a few seconds.
Okay. Thanks so much, Nathan. That was a lot of great information. We appreciate your time.
My pleasure.
Just to wrap it up here, please visit the new website at newconcrete.org for resources on lower carbon concrete production and placement. The website provides access to our sustainable concrete guides, frequently asked questions, webinar recordings, and more. The QR code shown here will take you to the ACI bookstore where you can purchase New's recently released low carbon concrete guide. Okay, and then we go to the last slide. Okay, and right here, we just wanted to thank you for today's webinar. Please join our next webinar, which will begin April 23rd, Powering Low Carbon Cement, Unlocking the Potential of Electric Arc Surface Slag, presented by EcoSem. You can go ahead and click the QR code or the link, and it'll take you to the registration for that upcoming webinar. And thank you again for joining. Have a great day.
Bye, everybody.